Check. Sir, I think something wrong with my other webcam. So today alone, I won't be able to turn on my face video. So, but you will see whatever I'm writing here. Yes, sir. Uh, yeah, okay. Okay, yes, sir. So I think we can start with yeah. So last time we solved questions, sir. I think solving one question is more than enough for me to see like how you are progressing, what's your idea, which area I have to emphasize, and which area I can let you study on your own. So this idea I have pretty much. So solving one more question won't be necessary. So that's what I wanted to say. Yes, sir. Yeah. So we'll start with order. So we'll start with first chapter. So we'll. Do you have any exam or something you have to prepare for tomorrow, sir? So can we hear until like I'll try to finish 7:30. But can you be here until like 7:45 or something if something take time? Mm. Yes, sir. So we'll start with this AS physics with physical quantities. Yeah. By the way, you can stop me anytime, sir. If you have any doubt, you can ask me. No problem. Okay, anytime. Yeah. Yes, sir. Can you see what's written here clearly, sir? Yeah. Super. Okay. So now I just want to check if the clarity is okay and you can see. Yes, sir. Oh, it's blurred. Okay. 1 minute, sir. 1 minute, sir. 1 minute. I'll check. Yeah, but I think that's a quality with uplink. Yeah. 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 Yes, sir. Sorry about that. Yes. Okay. So no problem. So I think you already know this details. So we are interested in physical parameters. Okay. So we can yeah, so I'll explain. So okay. So in IGCSE level, we would have learned them as quantities, physical quantities. Yeah. So a parameter is just maybe a mold out name. Something we can measure, something we can observe, something we can calculate, something just that's not just a pure number. That's what we call it as a parameter. Okay, sir. There is a rule that let's say that I want to convey something to you. I want to convey this can be qualitative or quantitative, but I have to make sure that you understand what do I mean, right, sir? So that for the quantities and physical parameters, whatever I am trying to convey. So which makes sure that this is conveyed correctly is units. For example, I want to let's say that I want you to buy some amount of something. For example, let's say I want you to buy a gold for me. I have to tell how much I want, right? I can't tell you this much or this much. This word is a the word this is like very arbitrary, right? This does not serve any purpose to our need. So I have to say, maybe please buy me 5 grams of gold or 50 grams of gold. So this is how parameters and unit work. But there is one more difficulty that you should know what is a gram. Yeah. So you have to understand what is a gram. So for example, I'll keep something in my mind that this is some gram. I must have conveyed this information earlier to you before I say I want you to buy 5 gram. So then only, for example, let's say that without, let's say you don't have any understanding of how much is gram, 1 gram. Without that, we do not have any meaningful discussion, right? 5 gram means nothing to you. So a group of scientists join together and form set of quantities. this is this, this is this, this is this. So they define seven basic quantities, namely mass, length, time, um, current, temperature, amount of substance, and light intensity. So these quantities were before this conference, but these seven were picked as uh, basic or fundamental quantities. Why? Because any of this quantity cannot be explained in terms of other. Can you see? Can you try to explain length in terms of mass, or can you try to explain time in terms of length? No. So these are called basic quantities. So why these are called basic quantities? These can't be derived in form of other physical quantities or from other physical quantities. So different countries, different region have their own style of measuring these quantities. For example, in India, you can measure masses in sack, or you can. Have you heard of padi, sir? One padi, two padi. Uh, yeah, they measure volume, and then by that they understand. They translate the understanding of mass. Uh, in Europe, they will use pounds, sack. Okay, but scientists, they have to use a single unit so that they can convey information very clear, like little more clear to each other without any doubt or confusion, right? That's the purpose this SI units were introduced, system of international units. So mass is kilogram, length is meter, time is second, current is ampere, temperature is Kelvin, amount of substance is mole, light intensity is candela, CD. Okay, and yeah, yeah, no problem, no problem. In AS level, you just have to know what is light intensity. That's all. You do not need to worry about the candela unit. We don't use. Even in your A level, we will not use light intensity candela unit. We will use only watts total power emitted by a star. So no need, no problem. So that's not a standard unit. It is a unit, but not a standard unit. Okay. So these are the basic quantities and their units. They are chosen arbitrarily. This much is this. That's all. So there is no background. Why 1 meter is this length? You can't explain it. But you can explain how much is 1 meter in terms of light this travel in this much amount of time. But you can't tell why this is 1 meter. That's clearly arbitrarily chosen. Yeah. Okay. So these are basic quantities. There are many other quantities we can form and derive using these quantities. Those are called derived quantities. Okay. A very good example is velocity. You can know that velocity is distance by time. Maybe, yeah. So volume, you can take volume is length, any volume, length into length into length. Okay. Sir, do you understand that we are talking about, uh, is it a power cut there, sir? You are still able to, yeah, super. Okay, no problem. Sir, can you see that when we discuss basic quantity, we are addressing this side, and this side, these are the units. So derived quantities also, you can form a quantity in terms of other one, sorry, at least two or more basic quantities. We call them derived quantities. They also have their SI units. For example, velocity SI unit is meter per second. You can convey velocity in centimeter per hour also, kilometer per hour also. But SI unit is meter per second. No, no, just SI unit. SI unit for a derived quantity. The quantity can be derived or basic, but they have SI unit. Okay. Sometimes people see through if something have SI unit, then it is also basic quantity. No, it's not. Okay. So one more example is, for example, uh, can you tell me any equation involving force, sir? Super. Mass into acceleration. Theoretically, so it should be kilogram meter per second square, right? But this is not SI unit. This is base unit. SI unit, we call it as Newton. So we can define 1 Newton is 1 kilogram, 1 meter per second square. Yes, SI unit. Super. Okay. So I hope I make sense. Is it clear, sir? Yes. Yeah. So, but over the time, whenever we come across a new chapter and new quantity, we will see what are their units and what is SI unit and everything clearly, more clearly. But as of now, I think this understanding is more than enough. Yes. Now, how to write a parameter? So, this parameter has, if you want to write a quantity or a parameter, this has two parts. So, one is magnitude and another one is unit. So, this unit is well defined in advance by the society. Yes, yes. So you have well established what is 1 meter, how much is 1 second, how much is 1 kilogram, everything. So we just take the advantage and we use the result multiplication. Okay, multiply by this amount, multiply by this amount. Okay, and in the magnitude part, we have you can, it's just a number. It can be number anything. Okay, you can tell anything. In the unit part, it can be meter, kilometer, hour. Distance also can be told in light year, anything. Okay. So here we have to understand something called a prefix in unit. So what is a prefix is, instead of telling 1000 meter, I can save the space by introducing one small letter called kilo. So I can write 1000 meter or I can write 1 kilometer. Both conveys the same meaning. So it's just a prefix, and we should remember this prefix very actually these are very few places in ASA level that we have to memorize certain values for certain numbers, certain digits. Learning the prefix is very important, and yes, 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 yes. So you want me to list here, sir? I yeah, okay. Yeah, so I think we can start with the lowest. S- all the lowest are conveyed in small letters, sir. All the negative 10 power minus, they are conveyed in small letters. Okay, so we'll start with yocto, small y. So this stands for 10 power minus 24. Septo, 10 power minus 21. Atto, 10 power minus 18. Femto, 10 power minus 15. So this femto is little important because this is about the order of diameter of atom. Diameter of nucleus actually. Okay, so pico is 10 power minus 12. Nano 10 power minus 9. Micro, so sir, actually micro is this is the micro. 10 power minus, yes, 6. And milli 10 power minus 3. Beyond that, we use centi 10 power minus 2, but we do not use deci 10 power minus 1. I don't know why they are not using deci, but deci is 10 power minus 1. Yes, okay. Mm. Yeah, yeah, we rarely use this thing, but sometimes they ask this unit conversion itself as a question. So that might that time it might be useful. Okay, so if we want to look at the uh, powers of 10 positive, then we can start with iota. Iota is small y, iota is capital Y. So this is, yes, 10 to 24. Zeta, capital Z, for 10 power 21. Exa, capital E. Here it's ATA, here it's EXA. So this is ATTO, this is EXA. So this is 10 power 18. This is petabyte. Have you heard petabyte, sir? Yeah, actually, in hard disks we have terabyte, right? Yeah. So 1000 terabyte is 1 petabyte. So tera we know that it's 10 power 12. Giga is 10 power 9. This is capital M, mega. So luckily it coincides that million and mega stands same number of zeros. So people sometimes call it million also, but the actual is mega. And kilo is the only exception. This use small k, small letter. Kbyte, kilobyte, kilo. And hecto, h. This we rarely use 10 power 2 and deca, da. So these three alone small letters in the higher side. Okay. Yes, sir. And we need we should be able to convert one unit from another unit itself is a good practice. For example, let's say that I am saying 1000 centimeter. Okay. Now I want to convert this into, I have to tell this in terms of millimeter. So how we can do? mm, -2, yes. So three-step process we can do. First, we can convert the cent into its actual value, 1000 into 10 power minus 2 meter. Then I want milli. So I have to increase 1 0 here. So what I have to do, 1000. If I have to increase 1 0 here, I can multiply and divide by whatever the number of 0 I have to do into 10 power minus 2. Okay. So this will go here and this will become 10 power minus 3. So the here, so it will be 10,000 millimeter. So for, yeah, but if you practice 2 or 3 problems, it will be easy. See, for example, 20 microsecond. Okay. Let's say this is 20 microsecond. We have to convert this into millisecond. Mm. S- So we have to write this 10 power minus 6 second, right? Micro is 10 power minus 6. 10 power milli is 10 power minus 3. So we can write 20 into 10 power minus 3 into 10 power minus 3. So I have split this 10 power minus 6 into 2. So this one I am going to carry as a millisecond. So 20 into 10 power minus 3 will be my number, whatever the number. So 20 into 10 power minus 3 millisecond. Now this is 10 power minus 3. This has to go 3 zeros this side. 1, 2, 3. So 0. 1, 2, 3. 0, 2 millisecond. Okay. Only the first problem will be little complicated, but once you understand, it will be very easy. Okay. And this is not a standalone problem. In first chapter, some of the problems you will find the answer, but part of the problem you have to convert into these units, so that we can do. Oh, yes, sir. Is it clear? Yeah. So this has to do with physical quantities of numerical magnitude and unit, and prefixes and basic quantities. So 1.1 and 1.2. Yeah. Okay. In 1.23. So you want to write something, sir? Is it? Can it turn? Yeah. Super. Okay. So this point alone, 1.2.1 in the syllabus. Use SI base units to check the homogeneity of physical equations. Physical quantities. Sorry. Use SI base units. to check the homogeneity of physical equations. Okay, so this is in general called dimensional analysis. Okay, so this is actually very simple, sir. Now the idea is, um, let's say that I am asking what is the distance between A to B. I am asking you this question: what is the distance? Okay, I am asking what is the distance. So maybe I am person P. I am asking what is the distance. Okay, you are person Q. Can you tell me it is 5 minutes? No, why? Why you cannot tell it's 5 minutes? Yes, because what I am asking is distance, which means I am asking about length. What you're telling is minutes, which is time. That's all. This is dimensional analysis in a nutshell. What's been asked must be provided. So whatever the quantity is in the left hand side of the equation, the same quantity must be found in the right hand side of the equation. That's all. This is the basic of dimensional analysis. There are multiple ways to, yeah, there are multiple ways to work on this one. Um, so the simple one being, let's say that I am asking you a length, you should give me a length. You can also, for example, in US, if you ask how far is one city from other city, they'll tell you 2 hours or 3 hours. How it is possible? Yeah, for example, let's say that someone want to go from one city to another city. Okay, they'll ask you how long. A typical US person would say 5 hours, but this person has asked only for distance, but he said in time. Still it's a reasonable answer, not because it's a US, but why? Super. Awesome, awesome, awesome. Speed is distance by time. This person asks for distance, so he tell distance is speed into time. Based on that, he'll assume that you are driving in a constant speed in the speed limit, maybe 80 miles per hour or 120 miles per hour. Let's say that city is 500 miles per from other city. If you are driving in 100 miles per hour, everyone drives in 100 miles per hour, you are going to reach that city in 5 hours. So the combination of unit is also possible in the other side, but the combination must result in the same whatever you are asking. Okay. So for example, okay, we know that velocity is meter per second. The other side it is distance by time. This is also meter per second. Okay. So it doesn't matter whatever the velocity it is, whatever you are measuring, it should have the unit of meter per second. That's all. So there is no exception. It can be velocity of a train. It can be velocity of a toddler crawling here. It can be velocity of electron. This has to have the unit of meter per second. That's all. Okay. So to find units of the derived quantities, we will use SI base units. It's very easy to, and it doesn't matter if you define this is the unit of one quantity. It doesn't matter where that quantity appears. It will have the same unit. Okay. Can we check? For example, we know that kinetic energy is half mv square, right, sir? Yeah. So can we check the unit? What is the unit of kinetic energy? So if I put it in square parenthesis, meaning that we are interested in its unit. Okay. So K is kinetic energy. Now, this is the number have the unit of 1. Okay. So any number, it will have unit of 1. People will say 0, but it's not 1. It will have unit 1. Okay. So in this case, number is half. This number will not have a unit because it's a number. What is the unit of number? 1. Okay. So number has unit of 1. What is this in kinetic energy? Half mv square. What is m? Mass. Mass is kilogram. And one of the main mistake many of the students do, mass, they intuitively they write as a meter. So they'll go wrong in plenty of ways. You should not forget. Yes. Mm, yes. So this is mass m. In the unit also there is a m. It's meter, and also milli also m. So we should be careful about these things. Okay. And now we learned that velocity is meter per second. So what should we have for velocity square? So it's meter per second the whole square. So you will get kilogram meter square per second square. So now this is the unit of kinetic energy. Okay. Now so one so actually the energy 1 kilogram into 1 meter square by 1 second square is SI base unit, but this is called 1 joules. So yeah, so every time we do not need to write. When someone asks 1 joule, we can just say 1 joule. We assume you take 1 kilogram 1 meter square per second square. That's 1 joule. Okay. Now let's take a different energy. For example, potential energy. So can you tell me what's the formula for potential energy, sir? Do you remember? Super. So it's mgh. Mass into g is acceleration due to gravity into height. So mass is kilogram, acceleration due to gravity is meter per second square. H is again, it's a length. It's measured in meter. So what do you get? That's all. Whatever we got earlier. Okay. It doesn't matter what energy. Yes. It can be binding energy of the nucleus. It can be energy of an asteroid hitting the earth. We don't care. It has to measured in joules. Okay. And this got to have 1 kilogram meter square per second square. Okay. You might be wondering, we talked about binding energy, but you must have seen the unit of EV, electron volt. Yeah. Then how that is possible? We know that in IGCC. Okay. So do you remember what is the definition of potential difference, sir? Voltage. It's actually energy per charge. Energy per charge. Energy per charge. So if we rewrite this equation, we get E equal to V into Q. So V is voltage, Q is charge. So electron volt is also unit of energy. Yeah. So this you get from this equation. V equal to E by Q. Okay. The idea is if you take one electron, put it in 1 volt of potential difference, and it will accelerate, right? So that time it will have 1 electron volt energy. Yeah, no, just take 1 electron, put it in a 1 volt difference of potential. It will accelerate. So it will carry 1 volt, 1 electron volt of energy. Yes. Okay. So actually 1 electron volt is 1.6 into 10 power minus 19 joule. Okay. So if you want joule value, you bring this. Is it right? 1 minute. 1 minute, sir. I'll check the value. Yeah. So 1.6 into 10 power minus 19 joule. Now, where does this number comes from? This is nothing but charge of the electron. Yeah, sorry, sir, I accidentally left the meeting. Yeah. So where does this number come from? This is nothing but charge of the electron. Okay, that's the idea. Hmm. Now, anything. Okay, maybe we'll take one more example. We know, have you come across this equation? Energy is force into distance. Work done is force into distance. So, yeah. So work done is nothing but energy. So energy and work done, they have, yeah. Now force into distance is Newton meter, but we already know that Newton is uh, so energy is force into distance. So m into a into d, right? So again mass into see, instead of mass I wrote meter. So kilogram into meter per second square into meter. So again you will get kilogram meter square per second square. So it doesn't matter, all energy. Yes. Hmm. Yes. So this is just one good example of um, how this dimensional analysis work. Yes, sir. Okay. Now, what is the purpose of this homogeneity of equation is you can find unknown quantities to some extent. What is that extent is? We'll see. Can I turn the page, sir? Yes. Yeah. Yeah. Okay. Now, to find the unknown quantity, and this has certain limitation and it has some applications also. First, first, okay. First, we'll discuss the rules. One, you can add and subtract only the same quantities. Okay. So add same unit, which has same unit. So addition and subtraction of physical quantities is possible only their units are same. In other words, only their dimensions are same. Okay. You cannot add meter with seconds. You cannot add length with time. That's the meaning. Okay. Let's take this equation. S equal to ut plus 1 by 2 a t square. Have you seen this equation, sir? Yes. So this is second equation of. Now what is this S? Displacement. So this has unit of meter. So whatever this side must be unit have unit of meter. Otherwise you cannot add. So what is this U? Velocity. So it has unit of meter per second. This time has unit second. So what you get? Meter. That's all. How about this guy? Half. He has unit of 1. Acceleration meter per second square. T square. So what you get? So only you can add same unit. You can add or subtract only the same unit. You cannot add or subtract different units. Okay, super. So let's take this equation. Please check with this also. Mm, super. Here also it's same, no problem. Mm, Here, that's all. So what you get in result? That's all. So you can add only the same unit. You can't add different units. Meaning that you can't add different quantities. Okay. However, you can multiply and divide any quantity. That can be done. You can multiply mass with length. You can multiply mass with time. You can multiply volume with anything you want. Okay, any quantity can be multiplied by with any quantity, but only same quantity can be added or subtracted. Yes. Okay. Now this is a rule in the dimensional analysis. It has some application also. So for example, you can find the unknown quantities. Okay, maybe I'll take the very famous example. Let's take a simple pendulum. Okay, so we'll take the simple pendulum and simplest case, no air resistance, no friction between the ceiling and the rod, nothing, just mass of the bob m, length of the thread, whatever it is hanging, l. Okay, and maybe it will go some angle theta. Yeah, okay, and we are interested in what will be the time period it will take to complete one orbit, so one oscillation. Okay, so let's say that this is what we are trying to find. Okay, now mass is here. By the way, so we have to establish how simple pendulum work. They work only because gravity pulling them down. In space, simple pendulum won't work. Okay, gravity pulling them down, and this lets it to oscillate like this. Okay. Yes, 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 yes. Mm. So however, we'll study in detail. But this for this understanding is enough. Yes. Okay. Super. Now, now let's say what is the quest here? What we are finding? Time period. So what is the unit we are looking for? Seconds. So we are looking for time period. We don't know the equation. Okay. We are going to form the equation using dimensional analysis. Okay. Now, what are the quantities we know? We know L, we know theta, we know M, we know G. Okay, that's all we know. Now, some combination of this is going to give me the time. Okay, so that's the idea. We don't know the equation. So right away, we are going to take this theta out. Why? Because it has the unit of 1, or it doesn't have. Yeah, it doesn't have. So this is also a limitation we will learn later. Okay, so we got to find whether it's LMG. What combination of LMG is going to be there? Okay, so this side we are looking for second. Here we have L meter. Here we have M mass kilogram. Here have acceleration due to gravity meter per second square. Okay, so is it possible for us to have kilogram? No. So this doesn't work. No kilogram at all. Yeah, if there is another quantity with kilogram, we could have put numerator and denominator so that we can arrange this in such a way, no kilogram. Yes, we could have done that. But here is no other kilogram, so no. Okay. Now we have meter and meter per second square. Meter and meter per second square. Out of this, what we want? Only second. So how we can take second? For example, super. Can I say like okay. So first this is G and this is L. Okay. Now let's try to cancel out M. Do we want meter here? So how we have to get, either we should put L in the numerator, G in the denominator, or G in the numerator, L in the denominator. Okay. I'm going to put G in the denominator. You are going to tell me why. What we will get? Meter per second square. Okay. So this has a unit of second square. That's all. What we are looking for? Second. How you will get second square out of second? So time period of simple pendulum is some constant. Okay, because do you remember we remove the theta, some constant into square root of L by G. So what we understand here is it is independent of mass. So it doesn't matter what mass we have, this is going to have the same oscillation. Okay, that's why in AS practicals they don't care about what is the different size of the mass or uh, different size of the bob. They just give yes. Okay, so this is also one drawback of the dimensional analysis or homogeneity is that we can't address log quantities, trigonometrical quantities or functions, and exponential quantities because all of their units are just one, or they are called dimensionless quantities. Dimensionless quantities. So if any of this involves in a equation, we can't tell precisely how much is that. We can just tell there is a constant. It's up to you experimentally to figure out what is that constant. And actually, they have figured out experimentally it's 2 pi. Yes, 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 yes. Also, this will be helpful to check if the equation is correct in paper 5 also A level. Okay. Yes. So this the one drawback is it cannot address log quantity. It cannot address sine or trigonometrical any trigonometrical function E. Okay. So second drawback is so the dimensional analysis is like our grandmother. Okay. Like have you felt that if you go and did something wrong and some terribly happened, she'll say எனக்கு அப்பவே தெரியும். So something like that. Dimensional analysis can tell when an equation is wrong, but it cannot tell whether the equation is right. So yeah, we did, but we are not sure about this guy, right? So if an equation is dimensionally wrong, it's wrong. If we can't find it. If an equation is dimensionally right, we cannot say it is completely right. That's also one drawback of dimensional analysis. Okay, why? Because let's say that this side second, this side also it has to be second, but this side it can be microsecond. This side it can be light year. How does we know? Okay, that's a problem. Yeah. So by the way, light year is measurement of distance. Yes. So it's measured of distance. Light traveled in 1 year. So how to calculate this? I think you already know this, yes, sir. Yeah. So uh, distance of light covered in 1 year. Mm. So I think it goes 3 lakh kilometers per second. So if yeah, so if it goes for 1 year, what is the distance it will cover? Yes. So that's about so can I modify this question so that this is exam pattern how they'll ask. Okay, so the same equation. So in the question they're asking what is the value of n. How you will find out? No need to use log. That's why dimensional analysis much simpler to use. One advantage. This side it's seconds. This side you have to get second. Yeah. So L is meter. So you will get second square. But what this side you want? Second. But this already have square. So what if I put in place of n, I will get only second. No, not y minus 4. Okay. 1 by 2. We have to take root, right? Root is 1 by 2. That's all. Okay. So theoretically, we just have to take root. But they are asking what is a number. So what is a number for root? 1 by 2. Actually, this is one of the question in S25 QP 12. This summer question. Yes. Yes. Yes, sir. Is it clear, sir? You understand the concept? Yes. Super. Yes, super. So we'll do one more exam style question and then we will move on to next topic. Okay, just one question. Yeah. Okay. Okay. Yes, sir. Now let's take this question. So I'm going to give you a equation, sir. It's um okay. So now A, B, and C are constants. Okay. V is velocity, T is time. B by T plus C. Should I write little big, sir? Yeah, yeah. Okay. Hmm. Okay. So A, B, C are constant. V is velocity, T is time. So we have to find what are the units of A, B, and C, or dimensions of A, B, and C. Okay. So please try. Let me know if you need assistance. Yes, 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 sir. Yes, sir. Why is that? Okay, okay. I see what you're doing. Yes. Yeah, no problem. I appreciate it. Okay, no problem, sir. See, what is V? Okay. So, no, no, V is velocity. Sir, this is not a equation. This is not a equation of motion. Yeah. Yeah, yeah, yes, yes. Okay, now please try it. No, no problems. No, no. If I give clue, you will do it. Okay. Now, what is V? Velocity. So we discuss only same quantities can be added. So if this is meter per second, what this will be? Yeah. So no, no. What is this quantity will be? What is this quantity will be? That's all. You solve the problem. This also should be meter per second. Hmm. Now A T is meter per second. We already know T is second, right? So we just want to figure out the AS unit. So what you will do? Move this here. So meter per second square. That's all. Yeah. Lucky coincidence that this is acceleration. Okay. Hmm. So now let's take. Please try. Super, super. Hmm. Yes. Super, sir. You nailed it. Okay. See, only same quantities can be added. So we know that t is time. So c also should be time. Okay, super. You nailed it. Okay. Now b by t plus c, which is nothing but time, is meter per second. So b by second is meter by second. So b is meter. That's all. So a unit is meter per second square. B's unit is meter, and c's unit is second. That's all. Yes, sir. Yeah, yeah. Mm. Yeah, yeah. I exactly that. That's how. That's where you went. Okay, super. Maybe I should have explained that this is not equation of motion. Yes. Okay, no problem. Okay. Yes, sir. Have you seen this equation, sir? No. Okay, so you are ready to see this one. This is called Newton's famous equation, gravity. Newton's gravitational equation. Okay. Now we have to find the dimension of g, or the unit of g. So what I'm going to do, I'm going to rewrite this equation. Right. Both m and m1, m2, they are masses. So force, we know that is mass into acceleration, r square divided by m. Okay. So I can cancel one m, right? So, so from this side, yes. So acceleration is meter per second. R square is meter square. Meet m is kilogram. So the unit of g is meter square. So meter cube, kilogram, minus one. So it's meter per second square, sir, not meter. Acceleration is meter per second. Second power minus two. So this is called gravitational constant. Yes, and it has the value of uh, I think 6.10 per third. Yeah. So 6.67 into 10 power minus 11 kilogram inverse meter cube second power minus 2. Okay. Yeah. Gravitational constant. So you should not mistake this for acceleration due to gravity, small g. That is small g. This is capital G. That g is just acceleration near a planet or a sun. This is universal gravitational constant. If you have two mass, we understand gravity works between masses, right, sir? If you have two masses, they attract each other, product of their masses, inversely proportional to the square of the distance by this constant. That's why it's called a universal constant, gravitational constant. Never change. Yes. In any space of the universe. Okay. Yes. Yes, sir. So the last thing we want to do is dimensional analysis. Have you seen this equation, sir? Super, very famous equation. Mass energy equivalence. Einstein's mass energy. E is energy, m is mass, c is velocity. So this would be mass kg into velocity square. So meter square per second square. So you get the energy. That's all. So we understand dimensional analysis once and for all. Okay. Uh, can we move on to errors and uncertainties, sir? Do you have time for errors and uncertainties? Yes. Okay. Okay. So please look at your notes. Let it sink. If you have any doubt, please ask. Hmm. Let me know once you're done. Yeah, yeah. No problem. Take your time, sir. Yes. Okay, super. So that's homogeneity of physical equations and quantities. So I'll give that's how we skip marks, sir. Yeah, okay. Yeah, and actually it is a very interesting topic. This was not given I would say enough weightage in the ASA level, but in CBSE and other boards it's very important. Yes, no problem, sir. Okay, so we have now we are at now errors and uncertainties. Okay, so before going to errors and uncertainties, we must understand what is the significance of this. Okay, uh, in AS and A level, we do not worry that much about errors and uncertainties, except the problems dealing with errors and uncertainties. But in real life, for scientists, any experimentation, this is very important. Okay, because any physical quantity or measurement, okay, it has a limit how accurate it can be. Okay, it has a limit how accurate and how precise it can be. So that fundamental limit we call it as uncertainty. Okay, and depend on our requirement, we'll choose this uncertainty. Okay, let's say that um, we are going to buy maybe what's groundnut. We want to buy groundnut. Okay, so, in shop, what you will ask? How you will ask groundnut? So you will ask, give me half kg or 1 kg. Okay, let's say this person shopkeeper measures the groundnut, and instead of 1 kg, 1000 grams, it says 1002 gram. Okay, so our desired value is 1000 gram or 1 kg. But the top and balance in the provisional shop, let's say it shows 1002 grams. Do you think he will look for this 2 gram and remove it? Because it doesn't possess any significant value. Okay, but will we do the same thing in the pawn shop, gold shop? No, because 1 gram is I think approximately $8-10. Yeah, here 6 7. Now it's 9,000. I think. Yeah, so definitely they are not going to do it. So depend on what's our requirement, we will take things little different seriously. Okay, let's say that we want to buy civil materials for building a new construction or civil work. Okay, will we be asking things in kilograms? So we will be requiring things in tons. So assuming 1 ton is 1000 kilogram, 1 metric ton is 1000 kilogram. Yes, so that's the idea. So what is our requirement? Based on that, we will choose instrument that gives that accuracy. Okay. So choose. Okay. So now this is uncertainty part. Now what is this error? So in general, we have two type of error. Actually, we have three type, but the third type is not required. Okay. So what one is systematic, another one is random. Yes. So we have two type of these errors. On mindset. Yeah. Now this systematic error is a error that has flaw with the system, not with the actual physics. Okay. Hmm. Yes. So in very common sense, these errors are by the choice of the instrument or by the attention span of the human being who is making the measurement. Okay. So for example, this can be categorized into instrumental error. Okay. So in instrumental error, A, you choose a wrong instrument or a inappropriate instrument. For example, I am interested in measuring thickness of a hair, single hair. Can I do it with a ruler? No, I should have choose micrometer or screw gauge. So if I am to measure the thickness or diameter of the hair, then I would say obviously 1 millimeter, because there are 1 millimeter is the least thing that you can measure. That's called least count. So it's called zero. Uh, so least, we'll come back to that. That's least count. Okay. So we have to choose appropriate instrument. One, choice of instrument. Second, so choice of instrument. Okay. Second, calibration of the instrument. Let's say that the same case, we want to buy groundnut, but already someone bought sugar. So some amount of sugar is there. If the guy add groundnut, will it be actual groundnut value? Ah, yeah, it will have the mass of the sugar also. So we should have either remove the sugar or tear the balance, so that, yeah. So this, yes. So we have to fix this. Fixing the problem with instrument is called calibration. Okay. So what is calibration? We have to fix, for example, you want to measure some distance, but the ruler is broken in the end. It starts only with 7, 0.7. So what we can do, we can break until 1 also if you want. We'll start measuring from 1. In the final value, we will subtract 1. So this is what we call it as a calibration. So we have to calibrate any instrument. If you take a thermometer, we have to put it in ice, see if it shows 0. We have to put it in a boiling water, see if it shows 100 degrees Celsius. Yeah. So we just make sure that this works fine. Okay. So that's instrumental. B is human error. I don't think we have to talk on this one. Okay. Not seeing it properly, parallax error, thinking something else, thinking about his girlfriend and measuring, he'll give wrong. Maybe he think genuinely he saw 9, but it's a value 8, so he made mistake. Okay, so it's not that he willingly done it, but systematic error. What are the errors that can be minimized, or systematic errors? Systematic errors can be minimized. Okay, so one great example is, for example, let's say that I have to measure the diameter of the ball. Should I measure it here, A, or should I measure it here, B? In B. Why? B is the diameter. But let's say that, yeah, looking away and then I'm measuring it A, this induces a systematic error. But this can be reduced by putting it actually B. Okay. So you understand? So these are the human errors. One very good example is parallax error. Um, Another is, for example, I have to, let's say that I want to measure time pendulum, so time period of the simple pendulum, and I am interested in the theta. Okay. So what I will do, I will hold the protractor in one hand and oscillate the simple pendulum other hand while chewing the timepiece or the clock in my mouth. That's how one person run an instrument, right? So this all will induce systematic error. What you should have done, put a separate stand for holding this protractor, shoot the video and measure the time period using high frame per second camera, or because our reaction time is will definitely going to affect the time period. Yes. Mm. Oh, that's next part. Okay. First part is now, despite of how careful you are, there is a limitation on how clearly you can measure. That is what we call it as a random error. For example, uh, this list count. Okay, let's take a ruler and measure some length. Okay, in the ruler, let's say it's 1, 2, 3, 4, 5, 1, 2, something like that. Okay, let's say our object ends here. Now, will you call it 4.5, 4, or 5? 4.5. Approximately, it's in the middle. But are we accurate? No, we can't be. So despite of we have the measurement, you cannot guarantee more than plus or minus this whatever the least scale it can measure. So 1 millimeter. No, 0.5 is too much. Okay, that 0.5 also exactly in the 0.5. Only if we have the microscope we can tell. That's a problem. So this is what we call it as a random error. So the error you can't minimize. So what is the only remedy? Do the experiment multiple times and take the average. Okay. So this is called random error because it is random, and you can't. It is a actually it is a universal fact that if you run any experiment twice, you will not get the same result. Except if we are doing AS practicals, we are expected to have same results. Uh, yeah, but why it is true is the sensitivity of our instrument is not strong enough or small enough to be affected by the planetary motions. Otherwise, we'll get different results every time. Okay. Yeah. So these are the errors. Now, why we are interested in error is, let's say that I am making a measurement. So this measurement I call it as a A. Okay. This measurement in total, can you see, sir? I am putting a small bar above the A. I am telling I am going to give you this measurement with how good this value is. Okay. So I'm going to tell you plus or minus. I can tell you in whether percentage. I can tell you. Let's say that I am measuring in this value. Okay, length of this bar. I can tell you length of the bar is 4 millimeter or 4.5 millimeter plus or minus 0.5 millimeter. I can tell you like this. Okay. This small part is called uncertainty. This tells you, this tells you how uncertain this measurement is, or how much how much you can trust this measurement. Yes, yes. This range, that is uncertainty. Okay. So this can be given in two values. One, it can given as a number, or can you tell me what percentage 0.5 in 4.5? Yeah, 11%. So I can write this as 4.5 millimeter plus or minus 11% also. So this quantity can be less than 4.5, less than 4 millimeter, or sorry, this quantity is more than what I am trying to convey here is I measure this quantity. Okay. This quantity is anywhere between 4.5, sorry, 4.0 millimeter to 5 millimeter. This is what I'm trying to convey by these two equations. Okay. So this is what we call it as a complete measurement. A measurement without this uncertainty has no meaning. You are not telling about, uh, most probably you are lying. Yes, yes, yes. Is it clear, sir? Every measurement will have uncertainty. So every measurement plus any calculated quantity involving this measurement will also have uncertainty. Calculation, any calculation that is calculated using this measurement will also have uncertainty. Okay, so any calculation, no problem. Any calculation involving any of this measurement will have uncertainty. Okay, yes, sir. Now, hmm, now we just have to understand what is accuracy and precision. That's all. You already know. I'm just reminding. Okay, so accuracy is how close to the actual value. Precision is how detail, how detailed the value. Okay, so one more thing we should understand, whether it is accuracy or precision, we can't tell accuracy or precision with one value. We can tell only if there are at least two values. Only you can tell when you compare two values, then you can tell which. Yep. That we can, let's say that. Okay, we'll come back to that point. Yes, you can compare two values to that value, then only you can tell. Yes. But you are right, absolutely. Okay, sir. Uh, so this is one thing, and so okay. So in this stage, I want you to um, I want to address on significant figures. Okay, so I guess this is good if we do before we do move into calculations of errors and uncertainties. If we address significant figures, it will be worth. Okay, now let's say that there is a person A, and this person A asks person B, "How old are you?" Okay, now B says, "I am 18 years, 6 months old." Okay, now C asks A, "Ho- How old B is?" See, there is another person C. Okay, looking, there is another person C asking A, "How old B is?" Now A says 18 years, 6 months, 3 weeks, 2 days, 5 hours, 6 seconds. Is it appropriate? Why? Okay, so leave about the 6 seconds. What about other? It is more accurate, but this is true. Ha, yeah. So how come A know about B is because B told 18 years, 6 months. That's all. So anything more than 18 years, 6 months, this is all made up by A. In physics, if you do made up, like if there is any makeup significant figures, you will lose marks. So yes, so whatever this is called a given quantity or raw data. Okay, so whatever the raw data significant figures, whatever the number of raw data significant figure, same significant figures only should appear in your answer. You should give this significant figure, three significant figure. Okay, you can give 3 plus 1 4 significant figure, because in calculation midpoint we can actually increase one significant figure, but if you give 5 significant figures, then it is wrong. Okay, do you understand, sir? Yes, please. Mm, yes. Yes. Super. Awesome. Okay. Okay. So that I'm going to give you the rules of the significant figure here. Okay. So, hopefully this cover your doubts. Okay. Now is it clear? So whatever the raw data given, you should follow that significant figure. This is very, very important in practicals and paper 5, paper 3 and paper 5. Because most people without awareness they lose mark only in significant figures. Okay. Now what are the rules or regulations to follow in significant figures? Okay. So one, um, any non-zero left side or right side without a decimal point is not a significant figure. For example, I'm writing like this. Now this has only one significant figure. Okay. This value is 800. That's different. But how many significant figure has one significant figure? This better you write. Nope. If there is no decimal place. Okay. You better write this as 8 into 10 power 2. That's all. Okay. But yes. So if there is uh 1 minute, I want to read this clearly. Okay. The trailing zeros in a number with the decimal points are significant figure. So this is 4SF. Decimal point, a significant figure. Okay. Yes. 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 Okay. Why I want to I want to emphasize on this. Let's say that I have a measurement that can measure up to this sensitivity, but it is naturally this value is 800.0. So how do I tell you about my precision of the instrument? Only by this way. Okay. Say, okay. Let's say that I'll give you another value, 978.6. This is also the same measurement. I utilize the same value. Now, how many significant figure it has? 4. Now, I utilize the same instrument to measure, and naturally my value is this. So this also have 4 significant. Mm. Ah, so whatever like this you are asking. This is a not significant figure. So only after decimal place. So okay. So if any value has the unit behind it, right behind it, then all the zeros also including the same value. If I write here 800 meter, then it has 3 significant figure. Why? Because I'm precisely telling it's meter. So it has a 3 significant figure. Yes, sir. Okay. So with unit it has. Okay. Now the question that you asked. Let's say that A is the quantity 500. This has only one significant figure. Okay. B is another quantity. Let's say that it is 25. Now it has two significant figure. Now we have to find one more quantity that is involving A and B. Okay. So now let's say that C is A plus B. A plus B is let. Okay. We'll do C is A multiplied by B. Now this will be the actual value is 25 into 500, 12,500. Okay. But the least, which one has the least significant figure? 1. So we have to give this answer 1 into 10 power 1, 2, 3, 4. That's all. That's how you round off. Whichever has the least significant figure in multiplication and division. So in multiplication and division, you will conclude your answer with whichever has the least significant figure. Now we will work out other example. Let's say A is 5.25, B is 6.8. So this has 3 SF and this has 2 SF. Now we have to do a quantity A divided by B. So we will get Yes. So the actual answer is 0.7720, but we have to give 2 SF. So only this and this are SF. So we cannot, no, no, we cannot just ignore this. We have to round it off. But 2 is less than 5, so we will leave it. If it is instead of 2, if it is 8, then we will write 0.78. That's all. So yeah, if it is 0.775, international rule is you have to look at the previous number. If this is a even number, then you amend by 1. If it is odd number, you leave it. Yes, sir. Let's say that if it is 0.775 and 0.785, okay, you have to rewrite this to 2SF. This you have to write it as 0.78. This also you have to write 0.78. Yeah, yeah, we can follow. But Cambridge is not sensitive to ask this question, so you do not need to worry. Yes, sir. Okay. Yeah. So the last thing that we want to, why this is very important is in AS practicals, we have to form a tabular column. So we will use instruments such as protractor, rulers, and everything. We should understand what is the number of significant figure. We can measure it in the ruler and measurement. We should use the same significant figures in our calculation. We can exceed by 1, but we should not exceed by 2. Okay. Yes. So when we add or subtract, their significant figures doesn't play a role, but decimal places play a role. So whichever has the least number of decimal places, you will follow that decimal places. For example, 50.01, 25.6. Which has least decimal places? Uh, So this has only one after the decimal. So you'll follow this result. So you will get 1657. So you will write 75.6. That's all. So let's say that we have 6.825 plus 5.2, maybe 5.25. How many decimal after decimal? How many places we should have? Only because this is the list too. So we'll add 7 0. Yep. Yes. Mm. So we will round it off. So answer will be 12.08. Yes, sir. Yeah. Super. Okay. So now that we are clear with the significant figures, I think we can get back to errors and uncertainties. Is it clear, sir? Yeah. By the way, there are more rules to significant figures, but not important for Cambridge. Okay. If you want, we'll discuss later. Yes, sir. Is it clear, sir? And please keep this in mind, sir. You should never ever give your answers in fraction in AS level practicals unless otherwise it's specifically asked. Why the big problem with the fractions is they underestimate the significant figures. They do not carry the value of significant figure. Yes. Okay. That's the reason. Yes, sir. Okay. Can we move to errors and uncertainties back, sir? Yes. Yes. Okay. Now, first I will explain theoretically, then I'll explain step by step with example. Okay. Now, let's say A is a measurement. If I put a bar, this is not a vector. This tells I have included the value of the uncertainty also. Okay. Now, let's say that I have a measurement A with this value. Okay. So now this is called measured value. This is called uncertainty. Okay. So if I'm measuring using directly measurement or instrument. So if a quantity is measured using instrument, Then the value is, okay, this is the, yeah, 1 minute, sir. Oh, is it so blur? One minute. I think it's internet problem, sir. 1 minute. I'll check the speed. Yeah, I think internet speed is good. I don't know what's wrong with this one. Now can you see it clearly, sir? Can you hear me, sir? Can you see it now, sir? Okay. Sir, I think it's a problem with the browser Safari. I joined in Chrome, now it's working better. Okay. Yeah, sorry about this. We'll fix this. Yes, sir. Yeah, okay. So now, let's say that I am measuring this quantity A using an instrument. Now, this A is measured value, and this delta A is, let's say that I am measuring everything perfectly, no systematic error. In that case, delta A will be least count. No systematic error. No systematic error. Okay, no systematic error. Then this will be least count. But is it possible in real life to measure using an instrument with no systematic error? So definitely no. So what we have to do, we have to take multiple. Uh, yeah, so least count. Okay, so what is least count? Is the lowest possible measurement we can make it in the instrument. Lowest possible value we can measure it in the instrument. Okay, so least count is nothing but lowest possible value we can measure in an instrument. This depends on instrument. Okay. For example, if you take a ruler, the lowest possible value we can measure is 1 millimeter. If you take a micrometer, lowest possible value we can measure is 0.001 millimeter. So it depends on the instrument. Okay. Yes. Now let's say that there is no possibility that we can make a measurement without systematic error. So we have to overcome this one. So what we do, we take multiple measurements. So what we'll do, A1, A2, A3. Three measurements I'll make, and I'll measure the average. How we will find the average? A1 plus A2 plus A3 divided by 3. I'll get this value, right? This is what I will call it as a mean. Okay. Now, in A1, A2, A3, you will have a highest value and lowest value, right? So let's say that A3 is lowest value and A2 is highest value. This can be any number, sir. It can be A1 also. This can be A3 also. It doesn't matter. Okay. So what you will do, you will take highest value minus lowest. Highest value minus lowest value divided by 2. This is what we call it as a range by 2. Yeah. So you will take the range. What is the lowest value of A you have measured? What is the highest value of A you have measured? Okay. Let's say that I am taking in measurement. Let's say the 56.3 centimeter one measurement I am making. 58.5 centimeter one measurement I am making. 59.2 centimeter one measurement I am making. Yes. Yes. So the lowest is 56.3, highest is 59.2. So 59.2 minus 56.3. Okay, 59.2 minus 56.3. 2.9 divided by 2. This is 1.45. Okay. Now we have to find the average of this value. We would have find the average of this value, right? So 56.3 plus 58.5 plus 59.2 divided by 3. So we'll get 58. Okay. Actually, this is 58.0. In the calculator, it was only 58, right? But we have three significant figures. So 58.0. So now how to write this value is 58.0 plus or minus 1.45 centimeter. Okay. That's it. That's how we score 2 marks in practical paper and paper 5. So there are multiple methods. You can use least count also using this. But if there are no systematic error only, we can give least count. No systematic. Absolutely no. You didn't make parallax error and you didn't lose your concentration. So you firmly attach the ruler until the end. It was same temperature. It was same humidity. You are in the same position last year. Then we can. This is what you must use in the AS physics practicals. Okay. Why? Because we are measuring it. Yes. So this is the first and basic step in. Uh, yes. Okay. Now let's say that I don't want to give this in value. They're asking what is the percentage uncertainty. So how to find percentage uncertainty? Let's say A is a quantity. It's denoted by this symbol. This is delta, small delta. Delta A percentage is delta A by A. Okay. This part delta A by A is called absolute uncertainty. Multiply by 100%. So 1.45 divided by 58.0. So this is, so we'll get 1.45 centimeter divided by 58.0 centimeter. Can you see that both has to be in same unit? So if both are in millimeter, you do not need to convert them into meter. But one is in millimeter, another one is in centimeter. You need to convert both in the same unit. Okay, so into 100%. So you will get 2.5%. In other words, this is 58 plus or minus 2.5%. Okay, to 3 SF, so 2.50 percent. Okay, what do I mean by this is I can trust this value for 97.5%. So that's our uncertainty. Yes, in percentage. So, mm, mm. Yeah, same way you will get only 2.5. Yes. Okay. So yes, if you is it clear, sir? Yes. Now the small part is called uncertainty. Okay. This part is called percentage uncertainty. Okay. This part delta A by A, this is called absolute uncertainty, but we do not need for our syllabus. Okay. Yes, sir. Mm. Yes, yes. S- Super. So the question is only if these values have uncertainties, we can have uncertainty, right? Huh? We measured 3 times and we got 3 different values. What it says? Okay, so it means that if it says 3 different times, 3 different values, mean it got some uncertainty. We are finding what is that uncertainty. Okay, yes, sir. The more time we can do, repeat the experiment and take the average, the more accurate value we can give. Okay, yes. If you are measuring simple pendulum's time period, means for each time we will do 10 oscillations and find what is divide by 10, find what is T1, and do again 10, find what is T2, do again 10, find what is T3, and average of T1, T2, T3, and find this method. Yes, is it clear, sir? Super. Do you need a break, sir? Yes, super. Okay. So the last part of the, can we move to next part? Yeah, super. So errors and uncertainties, the last. So this has to do with errors and uncertainties in measurement. Now we have to do errors and uncertainties in calculation. Yes, but it is easy. Once you understand, you can actually, it's just very easy. Okay. Yes. Okay. Now let's take two quantities, A, which is A plus or minus delta A, and B, which is B plus or minus delta B. Okay. So now I am going to say two mantras. These two mantras are more than enough to address any given problem in uncertainties. Two mantras. Okay. So first, in addition or subtraction. Okay. We will add uncertainties. Okay. One mantra. Yes. It is whether it's addition or subtraction, doesn't matter. If addition or subtraction, we will add uncertainties. Second mantra is in multiplication or division, we add percentage uncertainties. That's it. Okay, as simple as it. Uh, Everything will be covered in these two lines. Yes, 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 yes. That's all. Anything. Okay. Can I give example? Let's say, yeah. Let's say that I want to say C is A plus B. Okay. Wow. Now C value we can direct. For example, let's say that A is 5 centimeter plus or minus 0.5 centimeter, and B is 8 centimeter plus or minus 0.7 centimeter. Okay. Now I am telling C is A plus B. Okay. Now remember C we have to give in this format. C plus or minus delta C. Yes. Yes. So yeah. So this will be 5 plus 8 C quantity. So this will give 5 plus 8 is 13. Okay. So this will be 0.5 plus 0.7. So this will give 1.2. So C value will be 13 plus or minus 1.2 centimeter. That's all. Okay. And this is true for C is A minus B also. Okay. So in this case, it will be minus 3 plus or minus 1.2 centimeter. Whether it is addition or subtraction, we add uncertainties. That's all. Okay. Is it clear, sir? Yes. Super. Maybe I'll box this one. Yes. Okay. Now, what about this uh, multiplication or division? Okay. That's where this percentage uncertainty comes. Now, let's say that C is A times B. Okay. Wow. So, what kind of quantity C will be? A is in centimeter, B is in centimeter. So, what will be the unit of C? Centimeter square. So, C is indeed area. Okay. So, now we have to see in this format C plus or minus delta C, right? So, this is simply 5 into 8. So, 40 centimeter square. Okay. Now we have to find delta C. Now, what we said for multiplication or division? So, we have to add the percentage uncertainties. So, percentage uncertainty in C is equal to percentage uncertainty is A plus percentage uncertainty in B. That's all. Okay. 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 And look here. Whatever I'm writing, please look here. Then you will understand. Okay. What is percentage uncertainty in C? Delta C by C into 100%. So this is equal to what is percentage uncertainty A? Delta A by A into 100%. Plus what is percentage uncertainty in B? Delta B by B into 100%. Can you see all has 100%? So we can cancel them out. So you can write delta C by C is delta A by A plus delta B by B. If percentage uncertainty is directly given, you do this. Otherwise, we want only delta C, right? So delta C will be C into delta A by A plus delta B by B. That's all. Yes. So can you tell me what is C will be? Maybe 40 into delta A, which is 0.5 divided by 5 plus 0.7 by 8. So this is 1 by 10, 0.1 plus how much is 0.7 divided by 8 is 0.08. Yeah, 0.09 this is. Yeah, I think mm, everything has two SF, so we can round it up to 0.1. This will also have 0.1. So 40 into 0.2. So you will have 8. So my value will have 40 plus or minus 8. Okay. I think we are clear with that. Yes. So C is 40 plus or minus 8 centimeter square. Mm. Are you clear with this page? Yes. Okay. Let's say that let's take the same equation. C equal to A into P square. Okay, sir. And one more example, c equal to a into b cube. One more example, c equal to a power 4 into b power 1 by 2. Okay, this is indeed a power 4 into square root of b. Okay, wow. Now c is a into b square. What we will do? Let's say c is a into b. What we have done? Percentage of uncertainty a, percentage of uncertainty b. So can I write this as delta c by c equal to delta a by a? Can I write this a into b into b? You got it. So delta a by a plus 2 into delta b by b. Tell me for this. Mm, 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 mm. That's all. So delta a by a plus 3 delta b by b. Tell me in this case. Whatever in the power, it will come in front. So 4 into delta a by a plus, what is the power? B power 1 by 2. 1 by 2 delta b by b. One learning is whether it is plus or minus, we will always do plus. It can be a power 4 by square root of b also. Then this is a power 4 into b power minus 2, 1 by 2, technically, right? But we will just do delta 4 into delta a by a plus 1 by 2. It's always plus. Because whether you are multiplying or dividing, we always add percentage uncertainties. Sir, I also want you to understand why no 100% everywhere, because in both sides, so I cancel it out. Mm. I hope it makes sense, sir. Mm. Super. Okay. Can we do little problems so that? Yeah, sure, sure, sure. Yes, 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 yes. Yes, please. Mm. Mm. Okay, okay, okay. See, so this quantity is 0.7 by 8, right? So it is 0.7 divided by 8. Now it says 0.0875. Now in the numerator, we have only one significant figure. Denominator also, it have only one significant figure. So how you can round it up to one significant figure? 0.08. The next is 7. So 0.9. So I just want to round it to one significant figure. So I took this also 0.1. Okay. So if I didn't round it off, I would have got 0.09. So this is 0.1 plus this is 0.09. So I would have got 0.185. That's all. That's the difference. Yeah, yeah. Yes, 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 it is right. Yes, sir. Is it clear, sir? Yes, yes, yes. Okay. So now I just want to do some problems. Okay. So we have very good uncertainty problems. Mm. Okay. We'll do a simple problem first. Yeah, sure, sure. Sorry, sir. Sorry, sir. Mm. Mm. Sir, if you want to copy, let me know. Okay, I'll stop. No problem. Tell me when you're done, sir. Mm. Super. Awesome, sir. Okay. So first, let's do some easy problems. Okay. Let's say that there are two resistors. So I have measured one of the resistors value as 20 ohm plus or minus 0.5 ohm. Another resistors value 80 ohm plus or minus 0.7 ohms. What will be the total resistance? Yes. Mm, super. So this is R1 and R2. So 100 plus, actually in detail I can write like this: 80 plus 20 plus or minus 0.7 plus 0.5. So 100 plus or minus 1.2 ohms. Awesome. That's all. Okay. Now, now let's add, okay, same two resistors are connected parallel. Very interesting, yeah. 20 ohm plus or minus 0.5 ohm, 80 ohm plus or minus 0.7. Mm, mm, okay. So actually you can do the formula like this. Okay. So this will be R1 plus R2 divided by R1 R2. So you will get R1 R2 divided by R1 plus R2. Yeah, yeah. So you can directly rearrange it. Okay. There is a shortcut to it. How to solve this problem? Yeah, yeah. No problem. No problem. No problem. Okay. So first we will find the answer. So this is 80 plus 20 divided by 80 into 20. Okay. So 0.06. Is it only 0. No, it shouldn't have. Check the answer, sir. What answer it will have? No. Yeah. No problem is this is 1 by R. 1 by R is this value is right. We want to work for R directly. 16 ohm. First, just find the resistance value, then we will work on the uncertainty part. 16 ohms. Okay. Now, this is the equation. R is R1 plus R1 into R2 divided by R1 plus R2. Super. Awesome. Okay. But we have to break down very carefully. I'm going to break down this. Okay. So delta R by R is equal to R1 into R2. So we just have to add their percentage uncertainties plus R1 plus R2's percentage uncertainty, right? Now this is a single quantity. So R1 plus R2's percentage uncertainty is nothing but 0.7 plus 0.5. This is where we should not make mistake. Okay. So okay, let me break this, you will understand. Can I write this like R1 into R2 into 1 divided by R1 plus R2? Okay. So in this manner, it will be delta R1 by R1 plus delta R2 by R2 plus delta R1 plus R2 divided by R1 plus R2. Is it right? It is just 1 divided by R1 plus R2. So I didn't break it. I took it as a single quantity. So delta R will be R into delta R1 by R1 plus delta R2 by R2 plus delta R1 plus delta R2 divided by so R1 plus R2. Okay. So here, whether I write like this or delta R1 plus R2, both are same because 0.7 plus 0.5, that's all. Yeah, that is uncertainty in R1 plus R2, right? Okay. So how we can work out this? I'm going to continue here. Okay. So delta R combined will be R value we found as 16 ohm into delta R1 by R1. So 0.7 divided by 80 plus 0.5 divided by 20 plus 1.2 divided by 100. You got the value, sir? So 16 into 0.7 divided by 80 plus 0.5 divided by 20 plus 1.2 divided by 100. So you got 0.732, the total answer. So the combined value in the parallel resistance is 16 plus or minus 0.7 ohms. Okay. Now you might wonder, in addition it's just 1.2, but in combination it should have increased, right? But it has decreased. What is the percentage value here? 1.2 divided by 1.2 divided by 100. 1.2 divided by 100. Sorry, it will be actually 1.2 divided by 100 into multiply by 100. So percentage uncertainty 1.2%. Okay, here what is the percentage uncertainty? 0.7 divided by 16 uh, into 100. So we will get 4.3%. So it's 4.4% actually. Okay. Yes, it look like less, but it is more. Yes, sir. Super. Okay. Can we do one more problem, sir? Okay. Maybe let's do a little percentage uncertainty problem so you grasp the idea. Uh, yeah. Now, okay. So this is the equation. Okay. So I'm going to tell you S is measured with percentage uncertainty of 2%. T is measured with percentage uncertainty of 3%. Tell me the percentage uncertainty in C. Hmm. That's a beauty. Do you need values? What is the second mantra? That's all. We have to find delta G by G percentage. This is nothing but delta S by S percentage plus delta T by T multiplied by 2 percentage. So we want to find only delta G percentage. Yeah. So S percentage is 2 percentage plus 2 into T 3 percentage. So you will have 2 into 3 6 plus 2 8 percentage. Whatever the whatever the value measure G, it will have 8% percentage uncertainty. Yes, 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 yes. Hmm. Yep. Okay. So for addition and subtraction, we add the uncertainties. For multiplication and division, we add the percentage uncertainties. Yes, sir. Okay. Uh, can we do little more, slightly little more complicated problem, sir? Okay. Yeah. Okay. So diameter of a sphere, uniform steel sphere, its diameter is measured with the micrometer with this value. How many significant figures it has been measured, sir? Super. Okay. Yes. Now, find the percentage uncertainty in volume of the sphere. Yes. Okay. So now, okay. No, no. This is diameter. We don't need density. We just directly, I ask, what is the percentage uncertainty in volume? Okay. Yes, sphere. Hmm. Yes, sir. Okay. So how? Ah, yes. Mm. So actually, the formula is 4 by 3 pi r cube, right? We should not use r. If using r is we can do, but it's like touching the nose around the head. Okay, not required. And people also will try to find delta v by v, so they will first find v and then they will find this. That's also not necessary. What do we need is delta v percentage, right? So what we need is delta v by v into 100 percentage. So let's rewrite this formula for d. So v is 4 by 3 pi. Instead of r, I'm going to write d by 2 3 cube. So 4 by 3 pi d cube by 8, right? I don't care about these numbers. Yeah, d cube. So I want to find the percentage in volume. So d cube is there. Only 3. We'll finish our business and we don't care. We don't care. We don't care. We don't care. That contributes the 4 by 3 pi, 4 by 3 pi and this 8 everything gives detail to the numerical value of the v. We don't care. All we need is percentage uncertainty. So 3 into 0.01 divided by 5.00 multiplied by 100. Okay. So 3 into 0.01. Is it double zero or a single zero? Yeah. 5.00 multiplied by 100. 0.6 percentage. So percentage uncertainty in volume is 0.6 percentage. Yes, please. Hmm. That's why we do not need to find. The question is, what is the percentage uncertainty in volume? What is the percentage uncertainty? Delta V by V. Okay. So actually, I can prove that I can convert this into, first I have to do D equal to R by 2. Then I have to find the percentage uncertainty for this. Then I can cube this. I can hmm, yes. Hmm. Super. Let's say that we want to. Okay. So this is how you solve. Hmm. Yes. Now, yes. Okay. Now let's say that we want to use this formula. You are interested? Can we start a fresh page on this one? Okay. So this is sorry, diameter is measured in 5 plus or minus 0.01 millimeter. Okay. So we want to find the percentage uncertainty using this formula v equal to 4 by 3 pi r cube. Okay. So first we have to find r. R is d by 2. Okay. Wow. So we can simply find the r, 5 divided by 2, which is 2.5 millimeter. But we have to find delta r. Okay. We know that delta r by r is delta d by d. So delta r is r into delta d by d. So 2.5 into 0.01 divided by 5.0. Do you understand, sir? What's been done? So delta R is 0.005. Yes. So R is 2.5 plus or minus 0.005 millimeter. Okay. Wow. Now we have to find volume, percentage uncertainty in volume. So since again we will leave for all the 4 by 3 pi, this directly r cube. So 3 into delta r by r. So 3 into 0.005 divided by 2.5. into 100% for percentage uncertainty into 100 for percentage uncertainty. What do you get? Yep. Okay. Mm. Some people go further. They first find the volume. Volume is 4 by 3 into pi into r cube, 0.00, sorry, 2.5. We'll write in, okay. Okay. So what they do, 4 by 3, sorry, 3 into pi into 2.5 cube. Okay. Now this is the volume, 65 centimeter cube, and delta V by V. Again, they will find delta V. So delta V is V into 3 delta R by R. We don't have to. That's why the mantra percentage, add all the percentage uncertainty, go home happily. Why we need to do this? No, but you will get the same answer. It's not contradicting the formula. Okay, because whatever you are getting is nothing but percentage uncertainty R. This you bring here nothing but percentage uncertainty in V. So percentage uncertainty V is percentage uncertainty R. That's all. No, no. Okay, I'll explain, sir. What is this segment in R? Okay. If we bring this, what is this segment? That's what we started with. Percentage uncertainty in V equal to 3 times percentage uncertainty in R. That's all. Yes. Okay. So actually, people go this way because they do not completely appreciate the fact percentage uncertainty should be added in multiplication or division. Okay. Super. Yes, sir. Uh, there is one more errors. Sorry, vectors and scalars. That will take one class. Yes, sir. Yeah. So I think we can finish it with this one, percentage uncertainty. Uh, yes, sir. I'll be sending the photos, and this video will be there in YouTube tomorrow. Yeah. Okay. So just take a look at the notes and tell me if you have any doubt in your notes. Tell me if you have any doubt. Super, sir. Super. Yes. Okay. So 25th November 2025, we have completed with 1.3. Next class we will look at vectors. Okay, sir. Okay. Sir, by the way, is it clear? Do you like the class? How we proceed with the class? Okay. Really, I'm glad to hear that. Yeah. So, but we have discussed this already. The first few chapters will take extra time because we have to cover all the fundamentals. But once we pick up the phase, it'll go like really fast. I hope you are okay with the timing. If you are not, also please let me know. We can adjust the timing. No problem. Huh? Mm, mm. I see. Okay. So 5:30 is little early for you. Ah. Oh, I see. Okay. Okay. No problem. No problem. Yes, sir. Yes, sir. Okay. Yes, sir. Yes, sir. Yes, sir. Okay. Take care. Take care, sir. Ah. Super, sir. 6 to. Did we start at exactly 6? Yeah. Okay. Okay, sir. 6 to 8:15. Okay. Yes, sir. Thank you, sir. Thank you, sir. Take care. Bye bye. Yeah. Bye, sir.